Good morning to all. Welcome to the session for electromagnetic waves 18AC 55. We are discussing about model 1 portion. In the last class, we discussed Coulomb's law and field due to a line charge. Okay, in this class, we are going to discussing about the following topics. Myself, Professor Nandish SP, Associate Professor, Department of E&C, Government Engineering College, Carpet. Okay, in this class, we are going to discussing in detail about these topics, that is field due to continuous volume charge distribution, electric field intensity due to uniform sheet of charge, and electric flux density. Okay, first you take up field due to continuous volume charge distribution. Field due to continuous volume charge distribution. Here first you understand what is meant by volume charge. Before defining a volume charge, let us take up charge. We know that a charge may be in positive in nature or a negative in nature. Charge may be of any shape. If the charge looks in the form of point, it is called as a point charge. Suppose seems to be a line, that is line of charge. Suppose seems to be a surface, that is surface charge. Suppose it seems to be a volume, it is a volume charge. And it is a very minute in size. A charge is very small in size, but shape of the charge is considered and you can name it the corresponding charge, whether it may be a point charge or a volume charge. Now we are talking about field due to continuous volume charge distribution. The charge, it looks like a volume, is nothing but volume charge. Suppose you consider this figure. This shows electrical field intensity due to volume charge density. Volume charge density. Suppose you take up this figure. Here rho V. Rho is represent charge density. Rho V represent volume charge density. Taking a volume of the charge V here. V is the total volume of a charge and rho is the volume charge density value. In this volume V, let us take a small charge dq. Okay, this is a dq and this is a shape looks like a volume, that is a, and this charge dq, that is dq is nothing but small charge or a small fractional charge or differential charge you can call. dq generally referred as a differential charge or a small charge. Because of this volume charge distribution, the representation of this dq is rho v into dv, where rho v is the volume charge density and the corresponding derivative. See here, at some point P, what is the field intensity obtained due to this volume charge? You are find out. See here, this is a point P, and the distance from this point to this point is r. The electric field intensity obtained due to this single point charge is dE. Total charge is capital E, and this is a small fraction of charge due to a single volume charge, that is dE at the point P. In order to find a continuous volume charge distribution, let us consider this figure. See here, we define the volume charge distribution through the volume charge density rho v centimeter cube, and rho v may be a function of a space coordinates. The elemental field dE, or a small elemental field dE, at a point due to volume charge element dq can be found as shown in the figure here. Then you can write it as dE is equal to dq divided by 4 pi epsilon naught r square into vector ar dE is equal to dq, because we know that a field due to a single charge is given by q divided by 4 pi epsilon naught r square. Using that formula, you can define the elemental charge field dE is equal to dq divided by 4 pi epsilon naught r square into the vector ar. This is a unit vector showing the direction in which the charge is to be considered. See here, charge is to be considered, field is to be considered here, dE, in this direction. Now, because of this volume charge distribution, volume is nothing but it contains three coordinates. In three coordinates you are having a values. Say for example, the x value is having a certain x value, y value, z value, like that. That three coordinates, and the three coordinates will be covered by the three integrals, triple element integral. One is for x, one is for y, and one is for z. Totally, you can, instead of writing as this triple integral, you can write it as single integral, and under which we can write VOL. It indicates that volume integral. See here, charge is to be considered is dq is equal to rho v into dv. This is the charge, divided by 4 pi epsilon naught rp minus r whole square. Okay, rp minus r whole square, where rp and r the position vectors of the field point and the source point. You see that here, this is a source point and this is a field charge, right? Now this is the equation for the continuous volume charge distribution. That is, E is equal to volume integral dV rho v into dV divided by 4 pi epsilon naught rp minus r whole square into the unit vector showing the direction Rp minus R divided by modulus of Rp minus R. Okay, next coming to a topic, electric field intensity at a point due to an infinite sheet of charge. Infinite sheet of charge. I told that earlier, charge may be of any shape. Is suppose charge, I told that earlier, if the charge looks like a point, it is called as a point charge. It looks like a line, it is a line charge. It is a seems to see like a sheet. It is a sheet of charge. See this? Let us assume a infinite sheet of charge with a surface charge density rho s as shown in the figure. Here, see this? This is a one surface. Okay, this is a complete one surface over which one strip is to be considered. The value of the strip is dy dash, and this is placed from the z-axis y dash distance from the z-axis. See this? Divide the sheet of charge into differential width strips. The number of strips is str. Consider an incremental length dl at a point on a conductor. The line charge density rho l, is nothing but ds into dy dash, where rho s is the width of the sheet and dy dash is the strip to be considered here. Alright, rho l is equal to rho s into dy. See here, point to be considered only x value is existing. P of x comma 0 comma 0. Y value as well as z value is 0. Only x value is existing. See this? Figure shows an infinite sheet of charge in the YZ plane at a general point P on x-axis, and the differential width line charge is used as an element in determining the field at P. That is, dE is equal to dE is equal to dy dash into AR divided by 2 pi epsilon naught R. That is, you can say dEx, because only see this dEx indicates that only x value is existing. In the x direction value is existing. It indicates that x value, that is dx is equal to rho l divided by 2 pi epsilon naught r into cos theta. This is the basic definition of the line charge. From this you can consider, but we are talking about a sheet of charge. The differential electric field intensity at a point P is nothing but dEx is equal to rho s into dy dash divided by 2 pi epsilon naught into capital R. This capital R is nothing but square root of x square plus y square into cos theta. Then simplify this one. rho s divided by 2 pi epsilon naught. 2 pi epsilon naught is a constant. 2 pi epsilon naught is a constant. Rho s divided by 2 pi epsilon naught into x into dy dash divided by x square plus y dash square. Adding the effect of all the strips, we get Ex is equal to, here Dex, this is a differential field or a differential field or a fractional field, but here total field. Okay, very simple, in very simple terms you can see that Dex is nothing but addition of De1, De2, Det up to n number of points. Here instead of n number of point charges, you can have n number of strips. Adding the all the strips intensities or strip field, you are going to have a final value, that is EL is equal to Ex is equal to rho s divided by 2 pi epsilon naught. This is a constant value, and strips length is minus infinity to plus infinity x into dy dash divided by x square plus y dash square. Okay, simplify this one, apply the integration with the limits, that is rho s divided by 2 pi epsilon naught into tan inverse of y by x ranges from minus infinity to infinity. After simplifying this value, we are get rho s divided by 2 pi epsilon naught. Rho s divided by 2 pi epsilon naught. See, if the point P were chosen on the negative x axis, then Ex is equal to rho s divided by 2 pi epsilon naught into a unit vector. Ax cap or An represent the unit vector. That is, the field is always directed away from the positive charge. This difficulty in sign is usually overcome by specifying a unit vector An, which is normal to the sheet and directed outward or away from it. Then you can write it as the field intensity of a sheet of charge E is equal to rho s divided by 2 pi epsilon naught into An. This is the field due to electric field intensity due to a infinite sheet of charge. Remember the point, E is equal to rho s divided by 2 pi epsilon naught into An. This is the required value for the electric field intensity due to a infinite sheet of charge. Okay, I will review the thing. See this, you are taking a sheet of charge, you are taking a sheet of charge and this sheet of charge is divided into number of strips, so many number of strips. One strip is taken at a distance y dash from the origin, and this strip width is dy dash. Strip width is dy dash, and uh, density of this sheet of charge is rho s. Then what we done? Oh, okay, we are finding the value of dx, because only in x direction value is existing, in y direction and z direction value not existing. Then you can obtain the value. Finally you can have E is equal to rho s divided by 2 epsilon naught An. This is a formula. Then you pass on to a electric flux and electric flux density. Let us define electric flux and electric flux density. See, electric flux. Okay, to understand this concept, let us consider this figure. Let us consider this figure. With the help of this figure, let us define what is the electric flux and what is the electric flux density. See here, we are taking a metal conducting spheres. Here, this is the inside sphere. Inside conducting sphere, that is metal conducting sphere is nothing but metallic spheres having a small size compared to outer one, and this is a metal conducting sphere having a large in diameter. See this inner sphere having a radius r is equal to small a, and outer sphere having a radius r is equal to small b. Here small a and this is in small b. And in between these two spheres, inner and outer sphere, they were placing a insulating or dielectric material having a some particular dielectric constant, that is insulating or a dielectric materials here. Okay, let us consider let us consider here. Consider a concentric sphere having a radius of a meter, that is small one, charged up to a plus q coulombs. This sphere is then placed in another sphere having a radius b as shown in the figure. There is no electrical connection between them. There is no electric field connecting to this inner and outer sphere. The outer sphere is momentarily charged. Then it found that the charge on the outer sphere is equal to charge on the inner sphere. See here, very simple. See that the inner sphere is charged with a positive charge. The inner sphere is charged with a positive charge initially, and outer sphere is momentarily grounded. First the outer sphere is momentarily grounded, making the charge availability or available on the outer sphere, outer metallic conduct sphere, is making 0. Then the small inner sphere is placed inside without any electrical connection between these two spheres. There exists an insulating or dielectric material here. Okay, after some time, the negative charges, see the inner sphere is charged with a positive charge and outer sphere is grounded, there is no charge. After placing this inner sphere having a positive charge, in the outer sphere there exists a charges, negative charges in this boundary, outer boundary, without the electrical connection, and there exists a insulating material. There exists a flux, electric flux. Okay, this charge or a momentary charge is nothing but electric flux. This electric flux. This is referred as. See here, there is a displacement of charge in the opposite value, that is inner sphere positive value, outer sphere negative value, right? This is called displacement or displacement flux, generally called as a electric flux. Therefore, The electric flux represented by psi, this is equal to charge q. How much amount of the charge is there? The same amount of the electric flux is existing. Okay, exist or existing. That is, therefore, you can say that phi is equal to q. Charge is equal to electric flux. See here, figure shows the electric flux in the region between the paired charged concentric spheres. The direction and magnitude of D are not a function of the dielectric between the spheres. There is no electrical connection between them. The outer sphere is momentarily charged, then it found that charge on the outer sphere is equal to charge of the inner sphere. This is depicted by the radial lines, and this is referred as a displacement flux or electric flux. Therefore, I told that the flux is nothing but flux existing is exactly equal to charge in the sphere. Now we can define the electric flux density as if plus q coulombs of charge on inner sphere produces the electric flux of psi, then electric flux phi is uniformly distributed over the surface area 4 pi a meters. Here A is the radius of the inner sphere, where A is the radius of the inner sphere and B is the radius of the outer sphere. See this electric flux density is in the radial direction and as a value, that is for the inner sphere, electric flux density is denoted by the letter capital D. Capital D, that is electric field intensity for the inner sphere. R is equal to A, represent the inner sphere. The value is Q divided by 4 pi A square into the unit vector AR. Similarly, for the outer sphere, D outer sphere electric flux density D and radius is B, R is equal to B. Then for the outer sphere, okay, by mistake here inner sphere is written out. This is the outer sphere because of the radius is B for the outer sphere. The value is Q divided by 4 pi B square into AR. See that if the inner sphere becomes smaller and smaller, retaining the charge of q coulombs, it becomes a point charge. The flux density at a point r from the point charge is given by d is equal to q divided by 4 pi r square into ar. This is the basic definition of the electric flux density due to a single charge. Okay. See this electric field intensity due to a point charge in this phase is given by the equation E is equal to, where capital E is represent electric field intensity. Electric field intensity due to a point charge is given by the equation Q divided by 4 pi epsilon naught r square into AR. Therefore, in free space, there exists a relation between electric field intensity and electric flux density. D is equal to epsilon naught into E. Generally, D is equal to epsilon E. This is the relation exists between the electric flux density and the electric field intensity for a given dielectric material or a permittivity. Okay. It is see that this equation not applies only for the point charge, it is also apply for the volume charge also. In general, a volume charge distribution for the free space, instead of charge q, the same charge in the volume charge nature, rho v into dv. Rho v into dv, this is a representation of the volume charge. That is, E is equal to volume integral rho v into dv divided by 4 pi epsilon naught r square into ar for the F free space only. Okay. Now, the electric flux density D is equal to volume integral rho v into dv divided by 4 pi r square into ar. From the above equation, we can define the electric flux density for the free space for the given volume charge distribution. Okay, in this class we are learned field due to continuous volume charge distribution and electric field intensity due to a uniform sheet of charge and electric flux density. What is meant by electric flux and what is the electric flux density and the relation between electric field intensity and the electric flux density. These are the things we are discussed in this session 4. Thank you very much. Thank you.